Okay, thank you. Hello, everyone. Okay, the title of my talk is 3D Computational Welding Mechanics Applied to IN625 Nickel-Based Alloy. To go ahead.
Solves everything.
Okay. Okay, now it's work. Okay, this is briefly the summary of my talks. I'm content. I will start with a brief introduction. So I will try to introduce the importance of nickel-based alloy in general. Then I will describe you the geometry of the method, the result and discussion, and finally the conclusions. I want to start with questions. Will we be able to reach 50% absolute cut in emissions by 2050? Why demand of metal goods doubles? I would like to be optimistic, but the answer is that we have to work hard. Some expert claims that we have 30 years remaining to set up an industry that must operate at that times the efficiency of today oil industry in terms of the use of energy and carbon capture or carbon dioxide capture. So it's very challenging. In this scenario, nickel-based alloy plays a very important role because nickel-based alloys are related to polluting emission, thermal efficiency, and critical raw material as well. In particular, using nickel-based alloy, we can increase the temperature of engines and so the efficiency. Some experts claim up to 60%. And in turn, we can reduce the carbon dioxide emissions. So nickel-based alloy are related to different key sectors: advanced aeronautical turbines, energy production, naval propulsion, extraction of oil and gas, nuclear reactors, and hydrogen technologies. These sectors are all related to sustainability, as you know. And in all these sectors, welding plays a very important role. But not only welding, also the welding used as a repairing technique in order to increase the lives of components, of very expensive components. Think about a turbine blade, for example. So this is the goal of this work is to carry out, to build a numerical model of IN625 in order to have the possibility to optimize the welding process and in general to optimize the welding design using this kind of alloys. The materials is conventional IN625 as parent metals, and it was welded by using a filler metal, the AR nickel chromium molybdenum. This is the composition in the table. The joint was a butt welded joint with a thickness of 5 millimeters, and the two plates were welded by 3 pass. So it is a multi-pass welding. This is the parameter used in experimental design of the joints. This is the facility used for the calculation of residual stresses by X-ray diffraction techniques, and in the right side of this picture you can see the main important parameter using this measurement. About the numerical model, we applied the computational welding mechanic strategy. So, first of all, one has to simulate the thermal part and the thermal analysis. And the thermal analysis was simulated by using a Goldach heat source. The Goldach source is power density functions, as you can see in this picture, that travel along the weld line. And this is the equation of the Goldach source. Is a very classical Goldach source used for simulation of arc welding processes in general. Then for the boundary condition, we apply convective and radiative, use the Stefan Boltzmann law at the boundaries, at the surface. And we also exploit the symmetry of the components, of the geometry and also of the loads in order to reduce the number of the elements. So this one is adiabatic condition applied in this plane of symmetry. And of course, we use the temperature-dependent material properties. For mechanical analysis, we apply isostatic condition during welding. For the constitutive model, we apply the kinematic strain hardening model and temperature-dependent material properties as well, as in the thermal analysis. What is important to say is that thermal analysis and mechanical analysis are uncoupled. So first, one has to simulate the thermal analysis, and then the temperature history at each node is applied to the model in order to calculate stress and strain and the displacement of the nodes. This is the table that summarizes the main important parameter, geometrical, in particular parameter used for the Goldach heat source. Such parameters are calibrated by using a macrograph of the weld bead. This is the numerical model. You can observe that we have refined the mesh in the bead zone in order to capture the thermal gradients. And also we have divided the entire weld bead into three parts, three groups of elements, B1, B2, and B3, in order to simulate by using the activation function of the element to simulate the deposition of the three paths of welding. These are the results in terms of temperatures. In particular, in the left side, you can observe the three different fusion zones obtained during the three different paths, and on the right side, the video that represents that show you the variation of temperature during time for the three paths, pass 1, pass 2, pass 3. Then I go ahead to the result mechanical parts. In particular, in this picture, you can see the transversal residual stress or thermal stress after pass 1, pass 2, and pass 3. You can observe that the residual stress accumulated and increased during the different paths. So the greater the number of the paths, the greater the residual stresses or thermal stress that we calculated. And on the right side, you can observe the three components of the stress in the three directions, the transversal, longitudinal, and perpendicular residual stresses after welding. An interpass temperature of 200 degree are considered during the simulation, but also during the experimental part in order to avoid cracks during welding, hot cracks. This is the validation of the model, the comparison between residual stress in each directions, transversal residual stress, comparison between measurement and numerical results. So we found a quite good matching. So finally, for the conclusion, we developed a 3D model of the welding of IN625. We apply the computational welding mechanic approach, that is an uncoupled approach between thermal and stress analysis. Main result are that we were able to calibrate the heat source, the geometrical parameter of the heat source. Also, the model was validated by using residual stress measurements. The higher the number of welding passes, the higher the residual stresses. Okay, at the heat affected zone, this is very interesting, very important in my opinion. The heat affected zone is characterized by the highest values of transversal residual stresses. And you know that in this area, in particular near the weld toe, the crack generally starts and propagate. Okay, this is the final part. Thank you very much for your attention.
Thank you.